Probing relativity's limits. Ultracold atoms and tiny Ferris wheels. Probing relativity's limits. Ultracold atoms and tiny Ferris wheels. Albert Einstein's theories of relativity, published in the early 20th century, fundamentally changed how we understand time. They revealed that time is not absolute. Instead, it can be affected by motion. Specifically, clocks that move quickly or accelerate experience a phenomenon known as time dilation, where they tick slower than stationary clocks. While this effect has been observed in relatively large objects, researchers are now exploring a novel way to test it on an incredibly small scale using ultracold atoms and light-based structures. Setting the stage, time dilation and ultracold physics. Time dilation isn't just a theoretical curiosity. It's a core component of modern physics and has practical implications, such as the operation of GPS satellites, which must account for relativistic effects to function accurately. The current understanding is that the faster an object moves, or the stronger the acceleration it experiences, the more its time slows down relative to a stationary observer. This principle also applies to circular motion, meaning that moving in a circle can also cause time dilation. To investigate these effects on the quantum level, a team led by Vasilis Lembesis at King Saud University is harnessing the power of ultracold physics. At temperatures just a fraction of a degree above absolute zero, an incredibly low temperature, the quantum properties of atoms and molecules become much more controllable. By precisely manipulating atoms and molecules with lasers and electromagnetic fields, scientists can explore the effects of rotation and acceleration in unprecedented detail. The optical Ferris wheel and quantum clocks. In 2007, Lembesis and his collaborators pioneered a method for trapping and rotating atoms within the shape of a cylinder using carefully tuned laser beams. They playfully dubbed this structure an optical Ferris wheel, and their latest research suggests that these tiny structures could provide an ideal platform for observing relativistic time dilation in the quantum realm. Specifically, the researchers propose using nitrogen molecules as test subjects. They view the motion of electrons within these molecules as an internal clock. By observing the molecules spinning within the optical Ferris wheel, they hope to detect tiny shifts in the ticking frequency, essentially detecting the effect of time dilation. The potential accuracy of these measurements is astonishing. Researchers aim to detect changes as small as 1 part in 10 quadrillion. A new frontier for relativity tests. While the concept of using optical Ferris wheels is compelling, experiments using these setups have, so far, been relatively uncommon. This new proposal, therefore, opens the door to a new testing ground for relativity, where previously unexplored effects might emerge. The quantum nature of these ultracold particles may even challenge the fundamental clock hypothesis, the assumption that an object's acceleration directly influences its perceived time. It is important to check and confirm our understanding of physical phenomena in nature, explains Patrick Erberg at Heriot-Watt University. It is when we get a surprise, something unexpected, that we need to revise our understanding and gain a deeper understanding of the universe. Advantages and challenges. One of the key advantages of this approach is that it avoids the need for exceptionally high speeds, typically required to observe relativistic effects. Aidan Arnold at the University of Strathclyde notes, with the incredible accuracy of atomic clocks, the time change felt by the Ferris wheel atoms should be noticeable. Furthermore, the short distances traveled by the atoms during their rotation would provide ample opportunity for precise measurements. The controlled environment of the optical Ferris wheel promises to unveil new insights into the interplay between quantum mechanics and general relativity. The research isn't without its hurdles. A significant technical challenge will be preventing the atoms or molecules from warming up, which would disrupt their controlled motion and invalidate the experiment. However, scientists believe that the potential rewards, a deeper understanding of relativity at the quantum scale, justify the effort. By carefully controlling laser beams, the size of the Ferris wheel, and therefore the rotation of the atoms can be adjusted, allowing for testing of the time dilation effect for different rotation speeds. The potential of this approach lies in its ability to test the very foundations of our understanding of space and time, revealing new insights into the fundamental laws of the universe.